instead of a student seminar today, we're lucky that Liang Huang is in town and agreed to stop by for the day and tell us about recent success. So actually, now that you've, I was going to say, now that you've seen the previous title, you know what you need to know is that this is successful and you can go home. So Liang is one of the best people working on exact and approximate algorithms that combine dynamic programming and machine learning. Queens College, CUNY in New York. Before that, he was at ISI, USC ISI, working with people like Kevin Knight and David Chang. And before that, he was a grad student at Penn.
There's also a Google period.
Oh, okay. And in between, right, he was a Google researcher.
Yeah.
But he's one of the people who's come back to academia. Once they disappear into the Google maw, it takes wit and quick thinking to get out before you're chewed up. Okay.
Thanks, Jason, for a very nice introduction. So today I'm going to talk about something called discriminative training for machine translation. And the technical version of the title is kind of boring. It's like max violation perceptron and force decoding for scalable MT training. But you don't need to really understand that. But the kind of more intuitive version is that large-scale discriminative training for MT is finally made successful for the first time using the techniques I'm going to present today. So basically, discriminative training for MT is a very hard task. And here's the timeline. It started with Mert. Actually, it's 03 from Zach. But it can only tune a bunch of dense features, probably like 10 of them, but not like millions of them. And we know that for discriminative training to work, you have to have like millions of lexicalized features. And that's the case for parsing, that's the case for tagging, that's the case for many other NLP problems, but not the case yet for machine translation. And we'll see why it is very difficult. So people tried standard perceptron and didn't work out very well. And then people gave up on that line of work, which is basically training on the training set. And then they focused on just training on the dev set. That's, relatively speaking, very weird. Why would people focus on this line of work? Just training on the dev set was only 1,000 sentences, but for several reasons. First is kind of scalability. The MT is kind of slow, much slower than parsing, so people think you can't really scale it to the training set. And because you can only tune it on the dev set with only 1,000 sentences, you cannot expect to have many features because most of the useful features are lexicalized. And if you have a lexicalized feature, how often can you see a lexicalized feature in just 1,000 sentences? It's just definitely too sparse. So that's why most of these work are small scale. They cannot scale to many features. They can only do like 1,000 or 10,000 features, and they're mostly unlexicalized. So that's not what we want to do. And or some people use sparse features as one dense feature, and that's still not the right way to do it. The right way to do it is still to train it on training set, like in parsing and tagging and many other machine learning applications. But it took like 7 years for us to succeed finally on this line of work. So in our work this year, we used some variants of perceptron, which can train truly sparse features like more than 20 million features. And on the training, and we can scale it to the training set with like more than 100,000 sentences, much larger than the dev set, right? And that's why we can use so many features. But why? What's happening between these 7 years, and why we succeeded, and why Percy Liang's work didn't succeed? So what's happening here? And that's the most important idea, the take-home message in our work, which I'm going to talk about in detail today, is that our learning method, our learning algorithm, is a specialized perceptron version that learns to fix search errors. And the reason why search errors are so important in machine translation is because the search space is just prohibitively large. It's much bigger than those in parsing, much bigger than those in tagging. And for that reason, you have to use like approximate search, like beam search or cube pruning or whatever, to make it faster, to make it tractable. And because you introduce so much search errors, your learner have to adapt to those search errors. And if you just use a off-the-shelf like perceptron or Myra or whatever standard machine learning algorithm, they're well known to not to do so well on those huge search error problems like in MT. So in a sense, our learning algorithms have to adapt to the search errors and have to learn to fix the search errors. And that's why we succeeded after 7 years. It's not about the engineering tricks. It's actually about the learning method that makes the difference. Okay, so yeah, I talked about why standard perceptron fails. It's because, again, perceptron theory, like convergence proof and generalization bounds, and all those related online learning methods like Myra, is based on the assumption of exact search. So if you can perform exact search, then they can prove convergence bounds if the data is separable and so on and so forth. But MT, as I said, is never going to be exact search. And the severe search errors, for example, like if you do beam search from the input to the output, it's just a very tiny little fraction of the whole search space. So that's why it's called beam search. You can imagine there's kind of a beam into the thick forest, and it's very narrow. So that's why it's very bad search quality. And that's the way it is in practice. So the learning algorithm should actually fix the search errors. For example, if there's a huge search error here, you should say, I should not wait till the very end. I should stop and do an update so that I can fix the search error here right in the middle, right? Because if you go to the very end, you lose the signal. You don't know where to fix. And really, the problem is actually here, or maybe somewhere in the prefix, but not everywhere else. So in a way that we devised a variant of perceptron that is specifically designed for vastly inexact search. And so that we can fix search errors in the middle. And the way we do updates is partial updates, like on prefix, instead of full updates. And only that you can fix search errors. If you do full updates, we'll show that it won't work. Okay, and our results are very good. As I said, we had more than 20 million sparse features, and we can get more than 2 BLUE scores improvement over Merton Pro. Okay, so that's the general overview of the talk. Do stop me if you have any questions or comments. Then we'll go to the details. So I'll first kind of have an overview of MT training as structured classification using latent variables. Those might sound too technical, but it will hopefully be clear in the next few slides. And then I will talk about a special case of translation, which is the simplest machine translation paradigm, phrase-based translation, and force decoding, and then how do we learn to fix search errors, and some experiments. Okay. So structured perceptron is the kind of the starting point of the learning algorithm we're going to use today. It's a very, very old algorithm from the 1950s or 1960s from the Rosenblatt's perceptron. And it used to be binary classification or multi-class classification. And coding is extended to structured prediction, where you can have the structured input, like a sequence of Chinese words, X, and you want to translate it into a sequence of English words, Y. So that's structured input and structured output. And you can basically do the same thing, exactly same architecture. You do exact inference, you got a best answer. And if it's different from the expected answer, Y, then you do an update, right? And the update is basically rewarding the correct and penalizing the incorrect. So that next time if you see the same sentence, it's more likely that you'll get the correct output Y instead of some wrong output Z, right? So phi is the feature function. So you have some feature functions and so on and so forth, right? So that's all very easy. But the difference between these two is, it's huge, actually. So there's 2 challenges in applying structured perceptron to MT. The first one is that the correct derivation is hidden. So you know the X, you know the input, you know the output Y. But how does input translate to the output? Which word translate to which word? And how do they reorder? And what's the steps of translation? What's the derivation, basically, is hidden. And nobody's going to annotate that for you. You have tons of parallel text, bilingual, corpora, but there's no annotation of correspondence. So that's basically the latent variable. So basically, we have to extend structured perceptron to handle latent variable case. So that's the first challenge. The second challenge is that the exact inference box is never possible, as I said many times, because there are exponentially many classes. And here's only 2 classes or 10 classes for multi-class. And because there's exponentially large search space, you cannot afford to do it exactly. You have to do some inexact search. And it's well known that standard perceptron doesn't work well. So we have to fix that problem using some variant of perceptron. So that's actually the more important part of this talk. So we'll go over details of both 1 and 2 challenges. So sure.
Can you give us any insight into the relative importance of 1 and 2 as difficulties? So let me phrase the question in this way. We were talking this morning about this paper from MLP using GPUs for doing unproved parsing.
Right.
Now, if you could do unproved machine translation using GPUs, if you could get exact inference, would this talk be unnecessary?
I would say it's never possible to use GPU to do exact search on machine translation.
Let's imagine that it weren't possible.
If you
had exact inference, but you still had latent variables, would perceptron
it probably would,
the appropriate version of perceptron results?
Yeah, it would just work well without any of the tricks we're going to talk about today. Yes.
Thanks.
Yeah. Okay. Great. Yeah. So the real meat of this talk is about the second challenge. The first challenge is actually old, and people have done work on it. So which will be the next slide. The first challenge, okay, is MTS structure classification with latent variable. So you have a training example x and y that's annotated. How they translate, how does x go to y? That's hidden. Now in online learning time, in perceptron time, you take one example and you do decoding, right? So let's say, so during online training, you take this example x and you try to decode it, right, with your current weights, your current model. And this is your full search space. It's exponentially large. You've got one best derivation. That's the highest scoring derivation, d hat. And this derivation leads to a wrong translation. So that's different from, so this is actually dog bit man instead of man bit dog. And it's different from the reference translation. And what you want to do, you do an update. But how do you do this update? Well, the correct derivation is not annotated for you, right? So that's the latent variable case. And what you want to do? So you have to do something called force decoding, which is the space where every single derivation will lead to the correct output. So it's kind of constrained version of the decoding. So this is a very small subset of the full search space. The full search space is unconstrained. That's why you can have wrong translations. But among these correct ones, you use your current model to pick the highest scoring goal derivation. And then you can basically do an update between the two, right? So you basically want to promote this, so that make this score higher and make this wrong guy score lower. So that's your update. Reward the correct and penalize the wrong. So that's very easy. That is actually previous work from the previous paper. But that doesn't really work, okay, as I said. The reason is because of search errors, because you have a little very narrow beam. And in this narrow beam, the correct guy, from here, if you just move this derivation to here in the dash line, they actually already fall off the beam very early in the search. So really, the search error comes so early that you should fix the search error somewhere, roughly speaking, here instead of waiting to the very end. Because if you do the full update, it's not going to correct the problem, as we'll see. Okay, so that's the basic idea. Now, before we talk about how do we fix this search error, we have to talk about search. So how do you search for this best derivation in the full search space, and how do you search for the best goal derivation in the force decoding search space? That's the two search problems we're going to talk about. And then after that, we're going to talk about how to fix search errors. Okay, so we'll talk about the first unconstrained search problem first. That's basically MT decoding. So we use phrase-based decoding as an example. So here you have 不时与沙龙举行的会谈, which corresponds to Bush held talks with Sharon. There's a huge reordering between these two. And phrase-based translation is basically trying to cover each word once and only once. And it uses bit vector to record a space, to represent a state. So this bit vector means no word is translated so far, so every word is empty. And you can translate the first word, so covering Bush to 不时 to Bush. And then you can say a jump, make a jump of 2 and cover the last 3 words, 举行的会谈. Okay, that's this becoming this state. And gradually you can jump back to cover this 与沙龙 with Sharon, and you can have a full translation. So once every word is covered, you're done, right? That's just one derivation, one possible derivation. And you can say, I don't want to cover these 2 words together. I can cover one word at a time. You have another partial state, and then this state can cover the shalom again, and can have different paths. So there are many different paths from the start to the end that correspond to many different derivations in the search space, and the space is exponentially large. It's probably just, it's roughly speaking just traveling Selsam's problem, which is exponential. Okay, so that's the simplest case of phrase-based decoding. In practice, that's too simple. In practice, we have to integrate language models, and when we integrate language models, the search space will become even bigger. So previously we had states like just bit vectors. Now we have to annotate them, have to split them into kind of LLM versions, language model versions. We have to add the last word being translated so that whenever we extend, we can score the language model combination scores. Okay, for example, if you have with Sharon here, and then you have meeting with, So that's kind of the language model combo cost being scored. So this is kind of much larger space, and to make it practical, we use beam search. So beam search is basically saying that we organize them into, let's say, 6 beams, and each beam covers exactly the states which covers, say, 1 Chinese word, 2 Chinese words, 3 Chinese words, and so on and so forth, right? This time you can make it linear time, because if you have a constant beam width, then that's linear time. But this constant beam width introduces a lot of search errors, as we'll see. Okay, so that's the basic idea of phrase-based translation. Then we'll talk about force decoding, right? So we talked about this full search space case, and then how do we do this force decoding version, which you constrain that the search has to produce the correct output. This is actually a special case of the unconstrained version, whereas you have to have exactly the input and exactly the output. So basically, you still run the decoding as is, but you prune those states which has words that is not covered, not found in the reference. So only these 3 states are possible, and you just heavily prune the other states, because the search space is now much smaller. So this time is actually much faster. So that's one Go derivation, but in practice you can have a lot more. You can have millions of possible derivations to reach the goal. Okay, so for example, you can put Bush held talks, Wishelong, or Bush held talks, Wishelong, and so on and so forth. Every single derivation here produces the exact output. Okay, so that's called Go derivation lattice. And in practice, there are cases where it's impossible even to produce even one Go derivation. For example, in this case. So this is a sentence from Chinese to English, and in phrase-based decoding, there's a kind of a distortion limit which does not allow you to jump too far. So otherwise, the decoding will be too slow. So in this case, so United Nations sent 50 observers to monitor. That's so far so good. These are the prefix. But then on the Chinese side, you jump to the first iteration, which is the Sichuan Daxuan, right? And this jump of 5 is not allowed if you have a distortion limit of 4. So this sentence pair will be called unreachable in force decoding. In this case, we can use the prefix, which is kind of a sub-sentence pair, which is better than nothing. So in practice, a lot of sentences are not force decodable, and we just use the prefix as a backup to still get some training data out of these sentence pairs, because otherwise we'll just have to throw away tons of data in the training data.
So you might also get unreachability because your phrase have less.
Yeah. You also have the phrase limit problem, like you have bad alignments and so on. So this plot,
like unknown words.
Unknown words, yes. But you do it on a training set, so supposedly every word is known. So
on the input side, but you were trying to reach a particular output, so you might not know a particular translation.
Yeah, but that's part of a training set. So supposedly it's already known.
Oh, I'm sorry. Okay.
Right. Yeah. Okay. So on Chinese English. So this plot is about the reachability ratio, right? So how many sentence pairs are reachable, or in other words, have at least one force decoding derivation? Okay, so it depends on distortion limit. If your distortion limit is 0, which means you have to do monotone translation, well, it doesn't mean that each word is translated like 1 by 1. It means like each phrase translated by 1 by 1. So you still can do some local distortion within phrases. And if the phrase has like 5 words long, you have local distortions. But basically, for short sentences longer than 10. So even if you have unlimited distortion, you still have a lot of sentences. You still have some sentences that is not reachable. Now, if you look at Spanish, that's hugely different. That's completely different. So Spanish doesn't care about distortion limit, and there are much higher reachability ratios than Chinese. And it doesn't matter if you have 0 or 2 or 6. It's always like this. Do you know why? It's basically because Spanish and English are, roughly speaking, the same language. The word order are so similar. And there's a joke in this EMLP. There's a 20-year workshop, 20-year MT workshop, and the conclusion that they said why the IBM models were successful 20 years ago was because French and English was, roughly speaking, the same language. And that's a quote from Fred Jelinek, and that's not made up. So Fred concluded that the reason why IBM models worked was because they look at very similar languages. If they look at Japanese and English from the very beginning, IBM models would have been very different from the very beginning. Anyways, Spanish English are so simple, so easy that you only need to do monotone translation. That's basically it, right? So that's why Spanish English is not that interesting language pair to study with, and Chinese English is much more challenging language pair. And here's the statistics for Chinese. On the small data, full sentence reachability is only 20%. And if you add prefix, you can have more than 60% sentences covered. In terms of words, it's actually even smaller. It's only like 9% of words being covered because these are mostly short sentences, right? So, but if you add prefix, you have about 25%. If you move on to large data, these numbers all increase because the alignment quality has improved a lot because they are Giza alignments, and the Giza alignments are unsupervised. So if you have larger data, they can use about 1/3 of the data in the training. And the sentence reachability is also about 1/3. It's not very high, yes. Jason?
Can you remind us, you said this before, but I didn't understand it, why it is that even with unlimited distortion, you still don't get complete coverage of the training data?
Yeah, that's...
You're trying to do with phrases being misextracted.
Yeah, that's a very good point. So there's a phrase limit that you can only extract phrases up to, like, say, 5 words. And imagine you have a very bad alignment, which you have like very, so which forces you to extract phrases longer than 5 words. So you can say this sentence is basically not coverable by a phrase limit of 5, for example. So it's due to alignment errors and phrase limit.
But isn't it the case that you should be able to reproduce the bad alignment that you got at training time?
The alignment is given by Giza, and if it's everywhere, then all over the map, then you can't extract smaller phrases. So in the worst case, you have to say the whole sentence pair is one phrase.
The extraction heuristic doesn't back up.
That's right.
To individual words. Okay.
Right. So in the worst case, you have to extract the whole sentence pair as one sentence, which is a useless rule. Right. Any other questions? Okay. Very good. So this is how many derivations are there if a sentence pair is reachable? On average, of course, it's exponential. With this 6, there's millions or maybe like less than millions of possible derivations in the goal derivations. And these correspond to the latent variables. So we are dealing with a huge latent variable space. Okay. And now we're going to talk about how to learn to fix search errors. That's the kind of the meat of the beef of this talk. And so again, you have this picture. And there's a full search space. There's a narrow beam, which causes the correct guys to fall off very early in beam search. And how do you fix it, right? So, and here's a kind of example of the goal derivations falling off. So, for example, the blue guys are goal derivations, are potentially good prefixes. And it's possible that at beam 3, it doesn't make to the top 4. So it was not ranked high enough by your current model. So that's your model's problem, right? And it can also be merged with this equivalent state, and so on and so forth. So the idea is you should fix search errors somewhere here, not at the end. Okay? And how do we fix search errors? Well, there is something called early update from Collins and Rock. The basic idea is very intuitive. So you should fix search errors when the correct derivation, correct prefix fall off the beam. So for example, this is the correct or gold prefix. It falls off the beam at, say, step 5. And you should say stop and update. And you would do this update called early update, which is from the best incorrect prefix at step 5 towards the correct prefix at step 5, right? And you would skip the rest of the sentence. So this is kind of a very intuitive idea, but why does it work? And previously it was not known. People just know it works very well. But we had a proof in our previous paper why it guarantees convergence. And the basic, I'm not going to give you the mathematical version of that, but the basic idea is that here at early update point, violation is guaranteed. What is a violation? Violation just means that the incorrect prefix, this is the red one, incorrect prefix, scores higher in your model than the correct prefix, which should not happen, right? So if your model is good, then the blue guy should score higher than the red guy. So because you have a model error, there's a violation, and you should fix it here. Okay, so the violation is guaranteed if you do early update, right? Because otherwise, if the blue guy scores higher than the red guy, then it wouldn't fall off. It won't fall off. Okay, so early update works and can converge because it guarantees valid update, because each update is a violation. Whereas if you go to the very end, and if update at full sequence, which is normally what people do for perceptron, I mean, if you just use perceptron as is, off the shelf, then that's not guaranteed. Because it's very likely that at the end of the search, the correct sequence is actually scoring higher by the model than anything in the beam. Well, this sounds kind of weird. Why, it already falls off. Why would it actually score better? Because the global model might actually prefer this part of the sequence. In some sense, if you have exact search, if you can do exhaustive search, then the model is correct. The model actually prefers the correct guy higher than anything incorrect. But because you have to do beam search, and tons of search errors, the correct guy doesn't survive in the middle of a search. So it's kind of, the model is wrong if you give it this kind of search problem. So we should learn a model that is specific to the search error and robust to fix the search errors. So you should really kind of focus on here, not here. And intuitively, this update towards this direction is reinforcing the error because the model actually points up, right? That's why this is the best in the beam and this line is worst in the beam, right? So if the model already points up and makes a mistake, you should actually pull it back. So early update is actually pulling it back. So that's why it's good. It's a violation. And this is actually reinforcing the error. It doesn't fix the mistake, yes.
So we usually think of training these structured models by saying we want to make sure that the correct full structure scores higher in our model than the predicted.
Yeah, right,
or
right.
Scores higher in our model
than anything wrong. Yeah.
And then, but I guess what you're saying is that we really should be saying we
yeah.
want to make sure that
every prefix, yes.
Correct prefix
yeah.
scores higher than.
Exactly. Yeah. So to prove a convergence of early update, you really have to do what Adam says, that you have to assume the data is separable in the sense that every correct prefix is better than any incorrect prefix up to the same length at the same step, basically. Every single step, it should be the blue one should score the highest in the beam. Okay, so if you have that strong assumption, and then if you do early update, then you can prove the convergence. Yeah, that's exactly the case. So we have a much stronger condition. Okay, but in any case, a standard update, you cannot prove it's correct. It's always not guaranteed to converge.
You're not doing either of these, right? So what you just described as being the correct thing would be an even earlier update than you showed here. It would happen at the point where the red line comes above the blue line.
Right. So roughly speaking, maybe here, right? So early update is one instance which you can guarantee the convergence. But there are many other possible methods to guarantee convergence. Yes. Anything like any update that points down is correct. Any update that points up is incorrect. Yeah, basically. Right. Okay. So that's early update. But how do you generalize early update to machine translation to handle latent variables? So here we don't have latent variables. We kind of assumed there's only one unique correct sequence, but that's not the case in machine translation. So in machine translation, again, you have many correct sequences with goal derivations. Sorry. Wait. It was in a different. Sorry. Wrong slide. Okay. Anyways. Okay, that's early update. How do you generalize to the, sure. Oh.
Oops. Sorry.
Laptop or main PC?
Oh, that looks right.
No, should I? Oh, you muted? You unmuted? Don't know.
I unmuted the mute.
Okay.
Okay.
Okay, no problem. No. It's just, yeah. Yeah, sure. Yeah. Sorry about the technical problems. Again, this is the correct, sorry. This is the early update again. Early update. Now what we're going to do is to extend it to machine translation, where you have multiple correct sequences, or millions of correct sequences rather. Okay, so you have millions of correct sequences. Okay, every one of them is good. So how do you extend early update? Well, you would redefine early update as the point where every single correct prefix fall off the beam. In other words, roughly speaking here, all possible correct prefixes have already gone. In which case you can say, at this point, there's no hope of recovering any single correct derivation. Like, it's guaranteed that you have to produce something wrong, right? Because every single thing that is potentially good is already pruned, is already fall off the beam. Okay, now the early update is from the best in this step, the best incorrect in this step, towards the best correct in this step. So not here, but the correct derivation that is favored by your model, or the correct prefix that is favored by your model. So that's the simple extension of early update to later variable case. And you should stop decoding and skip the rest of the sentence again, right? So that works as well. But it's not working that efficiently. So learning wise, it costs you a lot more iterations to converge. And this is a well-known fact even in parsing. If you just do early update, it works a lot better than standard update, but it makes your learning much slower because you're only updating on a short prefix, right? So you can imagine at step 3, you fall off the beam. Okay, you update on these 3 words. You skip the rest of, let's say, 20 words, right? So you don't see much of the data, right? Of course, gradually, early update will move towards the right, but it still, skip too much of the useful information. So what we're gonna do? Sure.
Isn't it actually even worse than that? So if you may never actually be able to get past word 3.
Yeah.
What if you use this method for speech recognition?
Yeah.
So speech recognition is just noisy enough that a lot of the time, no matter what you do, you're never going to get past word 3.
Right. Yeah, that's also possible. Yeah. Okay, so what we do in practice is a better method called max violation, and max violation says that I don't want to do early update. I want to do the point much later on, so that it's basically the step or the position where the violation is the maximum, or in other words, the mistake is the worst, or the worst mistake, or the most violated constraint, or something like that. So the violation is defined as the distance between the best, the highest scoring wrong prefix at this point, so this is this point, versus the highest scoring correct prefix at the same step, right? So that's basically how much is the difference. And you do want to promote this guy to top and demote the wrong guy, right? So this distance is the amount of violation. And you fix the worst mistake in the search space. So basically, this point is the point where the search is most hopeless, okay? Or the worst in terms of quality. And later on, it's very possible that the global model would prefer the correct sequence. So if you do it at the end, again, it's incorrect. So if you do standard update, it's rather wrong because you're reinforcing the model errors. The model points up, and the update also points up. That's wrong. And the early update, max violation update, points down so that you pull it back. That's correct. Okay. And these cases are called violation fixing perceptrons in my previous work, and they're all guaranteed to converge. Yes, Jason.
Trying to ask so many questions.
Sure. No problem.
These are easy, I think.
Sure.
Is the size of the update related to the size of the violation?
The size of the update? What do you mean?
Well, so sometimes if you're using various kinds of loss-infused update methods, if the violation is larger, then you take a larger update step.
Oh, no, the learning rate is fixed to be 1, in a sense, right? So the update is always just the feature here minus the feature here. We don't scale the updates based on the violation.
Should you, or it doesn't matter because the beamwidth is fixed?
In theory, we shouldn't, because the perceptron theory just says if you do this kind of update, it's guaranteed to converge. If you scale the updates, I'm not sure how to prove it. So at least so far, it's easier just to have fixed learning rate. Yeah, we don't scale the updates. Yeah, and we don't have any parameters like learning rate to tune or something like that. Okay. Any other questions? There's one more possible update that's called local update, which is what Percy Liang and other people also use. So that's very intuitive as well. So basically, local update says I update towards the best in terms of BLEU score, or maybe sentence level BLEU score, BLEU +1, among my k-best list, among my m-best list at the end, right? So basically, that's the other candidates in the final beam. Maybe this guy has the best BLEU score, or whatever loss you define, then you update towards that. That's also correct in the sense that it pulls the model back, so it's not a wrong update like the standard update, but this violation is too small, and we'll see that this doesn't work very well either, but it's better than standard for sure. So yeah, so that's basically our method, and here's an example. So you start here, and at step 3, the correct guy falls off, and this is probably the early update place. And in step 4, the correct guy. In step 4, the correct guy was merged with the equivalent guy, so that's also a mistake, but that's not max violation. So let's say in step 5, we have a max violation, and we'll just update here instead of here. Okay, so that's the case. And if you compare structured perceptron with latent variable structured perceptron, is very similar. So we developed this violation fixing perceptron for structured perceptron in my previous work, and we just extended to latent variable case. And the only difference is now you don't have a unique correct prefix. You have many correct prefixes, right? Okay, but the same idea basically. And we think this method is a very general technique, and it started with perceptron, and we have 2 separate lines, 2 parallel lines. One is extending to latent variable, and the other is extending to handle inexact search. And we combine it to have a latent variable perceptron with inexact search, and you can use this to do many other things like hierarchical translation, semantic parsing, transliteration, right, for example, semantic parsing, for example. So the latent variable could be the syntactic parse, which is what Zettelmoyer was doing, right? And if you have inexact search, you can use our method like early update or max violation update, right? Okay, so any questions for the techniques? Now we talk about like feature design. So as I said, we have millions of features and they're mostly lexicalized. But feature design is rather kind of boring part of it's kind of mostly engineering part. But that makes our work have good scalability and good root scores. So we have to talk about that. And so the most important features in our work is the word address features, which is kind of inspired by parsing in the parse ranking work. So suppose you're currently translating this rule that is covering 举行的会谈 and translate to held a few talks, and you have already covered Bush to translate to Bush, right? And whereas these black words are not translated yet, okay? So what you can do is in this local window, in this local rule, you can have the first and last word in the Chinese side, the first last word on the English side, and also the previous word and the word after it on the Chinese side. So that's kind of the surrounding words. And these are all local features because the input X is given. So you can extract as many features as you want on the input side. But on the target side, it's dynamic. So you can only extract the current, those within the current rule, right? And you can have combos like you have these, you can have these 2. You can have any of these combos of these 6 local window features, and so on and so forth. So those are local features. We also have non-local features, but there are relatively few of them. So non-local features will go beyond the rule boundary. So say between 2 rules, so the 2 conceptual rules like rule bigram, that's one of the non-local features, and the current rule and the previous 2 words being translated. That's another non-local features. So far, we only have these 2 non-local feature templates. And we should have explored a lot more. But you'll see in experiments that just these 2 non-local features help us a lot. Almost give us 1 blue point improvement. Very few of a number of features, but very powerful. Now, we'll talk about experiments. So we have 3 kind of data sets: the small Chinese, large Chinese, and large Spanish, okay, English. And so these are the reachability numbers. So Spanish have a lot higher than Chinese for sure because the word orders are almost the same. 55% in sentences and 44% of words. And for Chinese, because the reachability is so low, we still add prefixes so to make them more useful. And these are the reachability plots that I showed before. And roughly speaking, these small data sets, we can use more than 10 times more data than the dev set. And in large, we can use more than 100 times more than the dev set. And that's why we can scale this to so many features, right? And in Spanish, also 30 times more than the dev set. That's the first time we can train it on training set, basically. Okay, so the next plot is probably the most interesting one. So we compared the four different learning methods. The max force, that's max violation, early update, local update, and standard updates. So local update and standard update are found in Percy Liang's work 7 years ago. These 2 are new, okay? And we can see that standard update, first of all, doesn't work, right? And why it doesn't work? Because a lot of the updates are wrong updates, invalid updates. So we'll show you details about that. And local is better, but not too good. It's still a lot worse than MERT, right? Whereas our two methods, max violation and early update, is better than MERT. And roughly speaking, 2 points better than MERT, which is a lot, right? And max violation is a lot faster than early update. Actually, if you run early update much longer, you can roughly speaking get to very close to max violation, but it costs you like about 3 times more learning time, right? The reason being that each early update is on a shorter prefix, so it learns less in each update. And mathematically, max violation also makes sense because the more the violation, the faster you can show the convergence bound in the proof. But that's some technical details. Okay, so this explains why President's work didn't work out well. And if we look into more details, say why the standard perceptron actually goes down instead of going up. And the reason is because you have tons of invalid updates. Invalid updates being like at the end of the day, you're scoring, the correct guy is scoring higher than anything in the beam, and your update is pointing up, right? And how many times does that happen? Right? You would think maybe that they're not very frequent, but actually they're so frequent. So this process, in standard update, how many updates are invalid updates? Basically mean pointing up. Well, if your beam is 1, most of them are invalid, 80%. Because if beam is 1, that means you're greedy. Your search quality is the worst, right? And you have a lot of these cases. And if you increase to 30, the beam size, which is the experiments that we do here, then you still have more than 50%. Roughly speaking, 60% of the updates being wrong updates. So that explains why standard perceptron just does horribly here. And we found this to be true in many other tasks like parsing, tagging, many other dependency parsing, phrase structure parsing, incremental parsing, bottom parsing, many other tasks. We always found that standard update does terribly because you have tons of invalid updates. That explains it, right? So previously people never look at this. So they just say, give me an update, and I will just update. And they never really ask the question whether this update is valid or not. So here we answer this question, how many updates are actually wrong and actually hurting the performance? Okay. Now, next we have parallelization. So if you just do this, it still doesn't scale to the whole training data. And we have to parallelize our perceptron. And here we use something developed in my group called mini-batch perceptron in this year. And it's shown to be much faster than the previous method from Ryan McDonald, which is called iterative pattern mixing. And many people have implemented this and found that it doesn't offer too much speed up. And in our case, we offer much more speed up. And it's also very easy to implement. So here we have the baseline here. That's in one core. Sorry, this is the baseline. Yeah, this is the baseline. If you just use a mini batch with 1 core, but mini batch of 24, even on a single CPU, if you just use mini batch, it still improves quite a bit. Okay, and then if you parallelize this line into say 6 cores or 24 cores, you got a lot of speed up, right? So in the end, we got about 7-fold speed up using 24 CPUs. So that's a lot, and that makes our work scalable to the whole training set. Okay, and here is the comparison of features, the contributions of features. So if you just have a dense features like those probabilities and those language models and so on and so forth, it doesn't actually work very well, right? It's actually much worse than MERT. It's about 2 points worse than MERT. The reason being, perceptron is not well known. It's not kind of it's not very suitable for those dense features where the feature scale of different features are so different, right? So perceptron is well known to be good for sparse features. So you have binary features, so just very small scale features. But if you have some probability features which are huge and some other features which are very small, if you mix them together, it's well known to be not working very well. So that's the reason why this doesn't work for dense features. If you add sparse features like rule ID, it improves, but still worse than MERT. The only time it improves better than MERT is when you add tons of word edges features. So it turns out that the word edges features are the vast majority of our feature set, more than 99%. And that offers like more than 2 points improvement over the rule ID. Rule ID doesn't have too much. Okay. And the last improvement is from the non-local features. As I said, we only have 2 non-local features. two-non-whole feature templates. So in terms of instances, only less than 1%. But that less than 1% features offered almost a blue point improvement over the local features. That's also very interesting. So we should explore that more. Okay. Now, if you compare with other methods like MERT and PRO, here's the comparison. So this is our max force. Okay. And MERT is not very stable. It's like, and if you run PRO, it's a lot more stable, right? So PRO dense is on the same features. It's more stable. But if you run PRO with many features, like millions of features, it's actually very bumpy. It doesn't do very well. That's well known. PRO, people know that it can only work on very small scale features. So the only time PRO is better than MERT is when you have medium scale features, meaning 3,000 features or 5,000 features. So we use 3,000 features, and it's slightly better than MERT, only by half a point. Okay, but in any case, ours is a lot better than any of these, and it's quite stable. So final results on the FBIS data for Chinese. So we have Moses. Okay, so 11 features. Oh, there's a bug here. So there should be the 2 digits after the blue scores, but for some reason this version doesn't show that. But in any case, it should be like 26.4 or something like that. But anyways, so we have a qubit, which is our system, and we use MERT as well. And with the same features, we have. Sorry. Why this? Oh man, that's. Sorry. 25.4 and yeah. And PRO, so you have to ignore these numbers, but the most important numbers are the last line. So if you just max force, and then you can train on a training set with more than 20 million features, you can have more than 2 blue point improvement over MERT. Okay, over MERT. More than 2 blue point improvement in both dev and test set over MERT. And PRO doesn't work very well. Okay. So that's Chinese. And for Spanish, roughly speaking, the same story. So for Chinese, you have both MERT and max force, and you have again 20 million features. And here we only use one reference because the data only comes with one reference in those WMT Europol data. So, but roughly speaking, we have 1.3 improvement and 1.1. So there's also another digit here which is not showing up in this version of the software. But anyways, so the difference is 1.3 and 1.1, but that's in one reference. And the general kind of consensus in the community is that if you get a 1 point improvement in one reference blue score, that would usually translate into about 2 blue point improvement in a 4 reference blue score. So in that sense, our improvement in Spanish is consistent with our improvement in Chinese. Okay, so to conclude, we offered a very simple yet effective online learning approach for MT. It's the first time that you can scale to the large portion of the training set with so many lexicalized sparse features for the very first time. And the other good thing is you don't need to define blue plus 1 or hope or fear derivations that is found in many other people's work. And there's no learning rate or any hyperparameters to tune. So it's very clean, just out of box, and you run it. And you can define any features you want. You don't need to worry about feature scale, too many features or too little features. You don't need to worry about that. And it has more than 2 points of blue improvement over MERT and PRO. That's considered a lot, right? And the 3 ingredients that made it work is, first of all, validation fixing perception, early update and max validation update. And second, the force decoding lattice helps. So in some previous work, they argued that the reason why it didn't work is because force decoding lattice has some bad derivations in it, like in Percy Liang's work. So he attributed the reason why his work didn't work out to be like some force decoding derivation is wrong in the sense that they use some bad rules to get a good translation. But we really don't know what derivations are good or bad, right? So we only know that it can produce the output or not. So in my case, we've considered every single derivation in the force decoding lattice to be good. So we don't say that this is just bad or not, because we don't really know, right? So these are just latent variable. We have no idea about latent variable, so we just take whatever that is there. And then the mini-batch parallelization scales it up to the bit data. So that's the 3 ingredients that made it work. And finally, again, the techniques that we developed here is a very general framework, latent variable perceptron with inexact search, and can be used to a lot of different problems. And we hope that it could replace EM for partially observed data. It won't replace EM like at all. It won't replace EM for all cases, because EM can also do like totally unobserved data, like those part speech induction or grammar induction, those Mariotto tasks. We can only replace EM for those partially observed data when you have input and output. Just how do you get from the input to the output? The derivation is latent, so we can only replace those partially observed data. But for even that is a lot. Okay, so to conclude, the take-home message is that if your learning is vastly inexact, like beam search or whatever, then you have to use some principled learning methods like max violation. So you cannot just use perceptron as a black box and say, I don't touch the decoder or whatever. To really fix the problem of the decoder, to fix the search error, you have to open the decoder and kind of couple learning and the search together. So the only reason that we get it to work is that we look at learning and search and combine them together. If you take learning and search separately, then it won't work for this very difficult task like machine translation. So again, learning and search should be together, and the learning should be learning algorithm should learn to fix search errors, should learn to improve the search quality. So that's the final story. Thank you. Yeah. Question.
So BERT training structured perception training optimize different loss functions.
Mm-hmm.
Do you think that the loss function BERT has is better or worse than the structured perceptron? In other words, do you think that the reason why BERT doesn't do well is because of optimization error?
No, BERT doesn't do well because of many reasons. First, it can only look at the dev set, right? It cannot scale to the training set for scalability reasons. And most importantly, MERT is still doing a full sequence update, right? So in a sense, it's all still doing the full sequence update like this. It doesn't break the decoder. Like it still treats decoder as a black box, right? And in terms of loss functions, yes, the loss function here is basically 0-1 loss. Very simple. There's no need to even do some like blue plus 1 or whatever, right? But MERT is very weird algorithm. I mean, it's very different from those perceptron Myra, and some people call it not even machine learning. So it's just a tuning, it's just optimization in a multidimensional space. It is well known not to scale more than, like, say, 10 or 20 features. But
so you think the problem is that MERT only works in lower dimensions, but there's
yeah.
Recent work at EMLP,
right.
which scaled it up to 3600
yeah, 3600 features is roughly speaking the pro medium experiments that we run, which is roughly sorry. Oops. Which roughly speaking those pro medium, it's a little bit better. In that EMLP paper, it's also like half a point better. It's very comparable to pro. So like in terms of features, in terms of performance, they are very comparable to pro. Whereas we have many more. We have millions of features, not just thousands of features, millions of features, and we can scale to the whole training set. Because in order to incorporate lexicalized features, you have to look at a much larger set. To look at a dev set, you can't use lexicalized features, right? So that EMLP paper was very similar to pro. So basically, that doesn't solve the problem. Yeah. Yeah. Question.
So I'm trying to think about how much of this is due to you being able to tune in much larger data sets, and how much is due to the larger feature set.
Mm-hmm.
And so I mean, those are related a little bit. But you talk about, you could have mentioned some experiments where, for one, you just ran max force on the dev set as another baseline, or
then you can use many features.
Right, but it would still give you a number, or maybe iteratively increasing the size of the training set you give to Pro, which can handle large features. Maybe we close the gap a little bit to max force. I'm wondering if you did any of those experiments.
No. So Pro and Merge, they all tune on the dev set. We don't even touch dev set. We only use dev set to tell us when to stop, right? Just that's a held down to know when which iteration is the best, right? That's why we in our iterations we just pick the one which has the best performance on the dev. So it's more like the traditional machine learning algorithm. Like the dev set is just held out. Whereas Pro and Merge they tune on dev set, which I don't understand because that's very easy to overfit on a dev set, right? So if we run max force on dev set, we have to have another kind of dev set or whatever tune set to tell us when it's going to stop.
Yeah, so I guess it's just the size of the dev set, then I guess. I mean, so tuning, I don't mean literally tuning on the dev set for max force, but I mean, just having a learning curve where you vary the amount.
Okay, so that's an interesting experiment to do, like how much data and increasing, you have more data and how much.
Yeah, if for Pro as well. I mean, I'm just curious.
Okay, so that should be a good experiment to do. Yeah.
And did you compare? I was surprised to see you didn't compare to Mira for tuning, because I've seen like with Colin Cherry and George Foster's work on the Batch Mira, the K-Best batch, they showed that generally it's a little bit better than Pro at least.
Yeah, it's very close to Pro. Again, it's only using like some features.
Yeah.
Right, and it's very difficult to implement. So that's why David Chen thinks his work is not replicable outside of himself, basically.
Yeah.
There's so many hyperparameters and so many little details to tune that it's really very hard to replicate them. Whereas here in our work, it's very clean. There's no hyperparameters. There's no plus one. There's nothing there. It's just central.
Okay. Yeah. I mean, yes, that is a real good work. And there's another question I can do for research. Actually, I lost it. I'll think. Okay, sure.
Can you say something about the size? I guess. Never mind. I was going to say like the size of the model that you learn there must be a weight associated with every feature. So I guess it's much bigger than the model. That's not very interesting.
So quick question. What about runtime for training?
Yeah,
and also
that's a very good question. So it is pretty slow. Of course, much slower than the Merge, because when we look at the dev set, we look at the whole training set, and it takes us like this point, about 2 days. So that Merge is done in a couple of hours. So that's a huge difference. Even on 24 CPUs, about 2 days. So we were trying to speed it up, but we were using Python, so that's not the reason. The Merge version we run is the
Anybody else? I just have asked questions already. So I'm sitting here trying to get my head around how you might use this as a general method in other problems.
Yeah.
And there are a number of funny things that are going on here, and I'm trying to understand which ones are relevant. So maybe I should just pose particular problems and let you decide which one to answer about. So one problem I'm thinking about is speech recognition, which is also a kind of translation problem, but one where you might have little hope of getting exactly the right answer or something. Another is a variation of machine translation where you have multiple references, which is often the case. So one easy way to handle that is that the choice of the reference is a latent variable or something, and so just like the derivation is a latent variable, and you're willing to pick any of them, but then it seems like you're kind of throwing away data. And a final example would be language modeling, where your input has size, is a translation of nothing to the entire sentence. So you said before that you couldn't use this to replace EM, but there are many, because all you see is output there and no input, but there are many cases where people have been trying to build generative models or other kinds of latent structure models where the goal is to produce part of the output that you covered up from the rest of the output. So in language modeling, you're predicting a word given the prefix that you've predicted so far, and then there's a tradition from Ando and Zhang and some of the stuff from Jeff Hinton's lab and so on, where you cover up a word and you try to predict it from its context, or you can imagine covering up a phrase, and maybe you're trying to learn parse structure or something that helps you do that. So all of these seem like settings in which you might try to get something like this to work, and I'm trying to figure out whether it would work, whether there's any theoretical statement that it should work, if there are material differences between this and the settings that you're looking at.
Very good question. So in these settings, the one with multiple references is the easiest. That doesn't involve much change. That we think about that problem because if you, like Matt said, if you train it on depth set, then you have more references, and you can actually have more higher reachability ratio. So you don't need to just one. You can just count any of them. So that is the easiest case. And in the speech case, if you cannot predict, if the reachability is
when you say it's easy, I mean, let me make it a little bit harder for you. So suppose none of the references are reachable.
Yeah.
And you want to do the thing where you say, okay, you want to get something with good n-gram overlap, thanks to
you can define
whatever.
oracle derivation. And
Sorry?
you can define oracle derivation as the closest to the references. And then you can just use that as a reference.
How is this different from the notion of a hope derivation or something, or it's just a hope reference, not a hope derivation?
Yeah, then you use hope derivation as as the correct derivation, and then you do force decoding.
I see.
Yeah.
Okay.
And then the difference between Mara and this one is you have to break the search in the middle, right? To take a search as a white box instead of black box.
Sure.
So all the other methods you take a search as a black box. And so the other two questions are much harder than I thought. Right?
I mean, I guess my worry would be if you're trying to predict without enough input, because your input is speech in the case of ASR, or your input is empty in the case of grammar induction, then you're not going to be able to predict the next word correctly in all sentences, because there is actual entropy. Remaining entropy, even given the input about what the next word should be. Multiple references is kind of taking a crack at that. Maybe it's not a big problem in practice. But I'm just worried that your policy space isn't good enough to be able to handle these problems as one-best problems. They seem like fundamentally problems where you're trying to match a distribution rather than match a single correct answer. And I'm trying to understand whether these methods would still have some applicability there if you generalize them to working with expectations over features instead of the features of a one-best or something. So you can think of the update in perceptron as being the zero temperature limit of the usual log linear update where you're trying to match the distribution. So I wonder if it's possible to take what you're doing again as a sort of like the zero temperature special case of a more general principle.
I think so, yes. So this is always max, and you can imagine being softer on max, like you have a little bit of soft average on it.
Right, but then what does it mean? What's the single point at which you stop? And what is it that you're treating? How do you measure max violation and so on? I mean, you maybe could do some of these things in expectations.
Yeah, exactly. You say the average is wrong versus the average is correct. And at that point, it's maximum.
And do you have an average stopping point? That's also a random variable.
Yeah, that's a good question. And you can sum up all these different updates, different steps, right? Yeah, we haven't done anything on that yet. Yeah, that's much harder to do.
It's worth thinking about. I mean, it might go through. I don't know.
Just doing the average is not fun. Any other questions?
So, have you thought at all about, or tried this applying it to hierarchical encoding?
Yeah, my student is actually working on that. I did an internship at IBM, and they asked him to implement this to hierarchies. And he's still working on that. And I know some other labs that are trying that on Hiro, and some labs already have successful stories, because this is quite easy to do, actually. As long as you have force decoding, and that's just very trivial. So.
Well, it's a little less trivial when you're...
Oh, it's definitely. For Hiro, how do you define max violation?
Yeah.
That's another story. So we had another paper at ELP, which defines the max violation for a CKY case. Whenever you have bottom up, it's not like left to right, right? It's hierarchical, it's hypergraph. And you can still define hypergraph max violation in this kind of bottom up case. But we did it for parsing at ELP. We will just extend to this for higher. So, yeah, technically, there's no problem.
Okay, well, let's thank Liang again for an excellent talk.